The first batteries, in the storage of energy sense of the word, not the row of artillery pieces sense of the word, were invented in the late 18th century, though inventors like Benjamin Franklin were fiddling with capacitors well before then, and those types of devices are themselves quite interesting. I did a deep dive into capacitors in episode 151 of the show, if you're curious to learn more. But for the purposes of this episode, what's important to know is that there are technologies that have been around for a while that utilize and store energy in different ways, and the versions that stored electrical energy in particular began to come of age in the 1700s, culminating with the first true battery, the voltaic pile, which was invented by Alessandro Volta in the year 1800. Practical batteries, which could actually be used for things rather than mostly just demonstrating up till then theoretical concepts, were developed in the mid-19th century. In 1836, a battery called the Daniell Cell was invented by John Frederick Daniell, and that battery, which had an operating voltage of about 1.1 volts, quickly became the industry standard for devices requiring electricity, including the newfangled telegraph networks that were weaving their way around the world at the time. Over the next several decades, many clever permutations of the same general concept were developed, all of which were inferior in some ways and superior in others, until, in 1859, the lead-acid battery was invented, which was remarkable because it could be recharged rather than being permanently drained when all the available chemical reactions were expended. A higher performing, easier to mass-produce model of this battery type was invented in 1881, and in the 1930s, the liquid inside many lead-acid batteries was replaced with a gel, which allowed another version, a sealed lead-acid battery, which is just what it sounds like, a permanently closed version of the battery, rather than one that you could open up and muck around with, was released, which allowed it to be used in more positions, scenarios, and industries, especially those in which the batteries would be handled by non-experts, who might injure themselves if they so much as touched an openable lead-acid battery. During this same period, dry cell batteries were evolving alongside, if not parallel to, the lead-acid battery. Dry cell batteries were often less powerful than their lead-acid kin, but were usable in a wide variety of situations right out of the gate, and could eventually be made quite small compared to the lead-acid variety. Early versions of dry cell batteries were invented in the mid-19th century, followed relatively quickly by a more modern version called the Zinc-Carbon Battery, which was first mass-produced in 1896. And it's this battery that made portable electronic devices possible. And interestingly, it was the invention of this type of battery, which became known as the D battery, that led to the invention of the flashlight, which replaced lanterns, candles, and torches, like fire at the end of a stick of wood torches, that were the only options for portable lighting up until this point in history. A strange, anachronistic technological situation in some ways. Here we have telegraphs and trains stretching across the landscape, and people are still burning beeswax and carrying around oil-powered lanterns to light their way. The first alkaline batteries were invented in 1899, and they had some advantages over the other offerings available at that time, but they were prohibitively expensive to produce, and thus did not really take off. By the late 1950s, however, a new method of arranging essentially the same components was developed, and that allowed these batteries to become competitive, and in many ways superior to the other available options. These alkaline batteries remain the most common and inexpensive options for many applications, and are basically, with some tweaks and upgrades, the same battery technology that you utilize if you stick a pair of AAA batteries into your TV remote control, or if you slot a battery into your flashlight today. As it turns out, though, another battery type would sweep in relatively late in the game and come to define the late 20th and early 21st centuries. Lithium was long thought to have immense potential in the world of energy storage because of all the available metals. It had the lowest density, the highest electrochemical potential, and the best energy-to-weight ratio. Experimentation began on lithium-based batteries in 1912, but a practical model did not come to market until the 1970s, though they were only really capable of powering very small devices with limited electrical needs, like cameras at the time. In the 1980s, though, innovations by American, Moroccan, and Japanese scientists led to the discovery of new materials suitable for use with lithium. If one wanted to use that core material to store more energy, better, and with greater stability, and with reliable rechargeability. Japan-based Sony put this new battery, which was called the Lithium-Ion battery, on the market in 1991. And in 1997, an even newer version of this battery was released, which changed up the composition a bit and rearranged the internal components to allow the battery to be more flexible, rather than needing to be tucked inside a rigid metal casing. This meant that not only was the lithium-ion battery powerful and rechargeable, it was also possible to reshape it in all kinds of ways. So it could be custom fitted to the devices that you wanted to make, allowing for all kinds of new form factors of personal devices in particular. This is the innovation that allowed for the creation of hardware, like portable computers, mobile phones, drones, and smartwatches. What I'd like to talk about today are the downsides of battery-based energy storage, alternatives to this method, and what the future might look like as we find ourselves not only increasingly capable of generating energy in new ways, but also capable of cheaply and reliably storing that energy for the moments we need it most. You're listening to Let's Know Things. I'm Colin Wright. If you're finding any value in Let's Know Things, consider becoming a patron at patreon.com/letsknowthings. By contributing any amount of money that makes sense to you per month, you gain access to a separate feed for the show, which is call to action free and which contains an additional episode each month. But you also help me support and sustain this show. I'm able to commit the time that I do to this podcast because of folks who are contributing to its perpetuation. So if you're able and if you're enjoying what you hear, pop on over to patreon.com/letsknowthings or to letsknowthings.com and click on the contribute button if you'd like to help support the show but are looking for an alternative to the Patreon option. A huge thanks to everybody who's already supporting the show in some way. That means a great deal. Thank you very much. All right, let's get back to the show. The article I'd like to start with today comes from IEEE Spectrum, which is a magazine produced by the Institute of Electrical and Electronics Engineers, and it's entitled, "How Inexpensive Must Energy Storage Be for Utilities to Switch to 100% Renewables?" This piece is about a recent deal made by the City of Los Angeles to build a solar power project that comes with a supplementary energy storage system. In practice, that means alongside the 400 megawatts of solar power generation, they will be capable of storing 1,200 megawatt hours of excess energy in a lithium-ion battery-based storage setup. And some terminology that will be useful here, I think. A watt is a unit of power, equal to 1 joule per second. And a joule is another unit of energy, equal to the energy transferred to an object when a force of 1 Newton acts upon that object in the direction of that force's motion over a distance of 1 meter. It's also the amount of energy dissipated as heat when 1 ampere electrical current passes through a resistance of 1 ohm for 1 second, which kind of makes things more complicated than clear, I think, as all of these measurements are based on measurements of other things, which themselves are not necessarily intuitive to non-physicists. So for the purposes of this conversation, just know that a watt is quite small in terms of electrical power, and although it's not the smallest measurement, there are attowatts and femtowatts and picowatts and nanowatts, it's also not terribly potent by today's standards. A 100-watt light bulb for instance, which is a common power level for old-school light bulbs, uses 100 watts of electricity to operate. That's the scale that we're talking about here when we talk about watts. 100 of them light up an older model light bulb, while somewhere in the neighborhood of 5 to 15 of them will light up a typical LED bulb. A megawatt is 1 million watts, and at this scale, at the 1 million watt scale, we can do a lot of things. It's a decent-sized chunk of energy that can power server farms and submarines, super colliders and very large lasers. Many of these machines use multiple megawatts of energy. A high-powered electric train, for instance, will usually use 5 or 6 megawatts of energy to keep itself chugging along. But that's the order of magnitude that we're talking about when we talk about megawatts. It's big stuff that requires a lot of power. It's a substantial amount of power. On a more local, human scale, a megawatt of energy can be as high as 1,000 homes worth of power, though on average, nationwide in the United States, because of the difference in energy consumption and energy loss along power lines, the actual number is closer to 200 homes per megawatt of energy on average. So going back to the system being built in LA, the solar panels will produce 400 megawatts of energy and will be able to store 1,200 megawatt hours of energy, which means 1,200 megawatts for an hour, or 1 megawatt for 1,200 hours, or somewhere in between. It's a measurement of energy provided over time. This build-out is part of the city of Los Angeles' commitment to achieve 100% renewable energy by the year 2045. And it's a decent step in that direction, but if you do the math on that, even without the possible outcomes in terms of how many homes and other energy consumers it feeds, it's still just a drop in the bucket in terms of what will be needed to provide backup energy or buffer energy during periods when the sun is not shining, when the wind is not blowing as strong as it needs to blow, when renewable energy sources are not actively providing renewable energy, which is a gap that needs to be filled if these sources are going to become the source of energy for Los Angeles and the world. So this project is a relative drop in the bucket, but it's not nothing, and enough of these projects combined is how you make change on scale happen. But unless we manage to build some kind of very efficient smart grid, capable of sending spare energy where it is needed on the fly, capable of shuttling electricity from energy-rich places to non-energy-rich places, algorithmically, as is warranted, to optimize the flow of watts, these types of storage systems will remain a requirement to make these types of clean energy projects practical. And even if we do get a smart grid in place sometime in the next decade, it's likely that such a system would only be fully functional if there are numerous energy storage centers located around the country, around the world even, to store excess energy when one area that is covered in solar panels has a particularly sunny day, while another, which is more dependent on wind energy, has a stagnant couple of hours and could use an energy top-up. The idea is to stash excess energy when it is not needed, so that it doesn't go to waste, and so that it's available when it is needed. And we will need building-sized batteries to make that happen. The question of energy storage cost, though, is an issue, because especially within our current paradigm, where fossil fuels remain economic competitors, if not ecologic ones, these projects need to be justified in terms of cost, not just long-term ecological benefit. And that means figuring out how to build storage for energy alongside the things that allow us to collect that energy, if we want renewable energy alternatives to become the default, rather than the outlier, the exception. In this article, experts posit that energy storage would need to get into the $20 per kilowatt hour range if we want the grid to be 100% powered by wind and solar, something that is possible in many countries and across many regions of the United States in the near future. That price, though, would be quite ambitious for our current best-known solution to this problem. Lithium-ion battery storage systems are the current hotness on the market, with entities like Tesla building facilities large enough to provide backup power for entire cities, and angling to build yet larger setups in the near future. They also have home and office building scale versions of the same, setups that seem to be relatively popular and could absolutely have a role to play in this smart grid-like system that we're trying to build. But on the cheap end, lithium-ion battery-enabled energy storage systems only reach $175 per kilowatt hour in 2018, which is good compared to higher prices in previous years and compared to some other alternatives. But again, experts are saying that needs to get down to $20 per kilowatt hour if we want to go full-on renewable, based on our current economic environment and other variables. Part of the why behind that number is that dollar for dollar, fossil fuels and especially nuclear energy is fairly inexpensive, and it provides gobs of electricity for utility systems on a consistent basis. These things are not limited by the wind blowing or the sun shining. But fossil fuels have obvious climate-related issues, not to mention the pollution-related ones, and nuclear energy is not a sufficient long-term plan to many experts, at least not as the core of our energy system. Because at the moment, at least, it is not truly green. There are byproducts that are dangerous and difficult to deal with, and there are security concerns. And at least until we can come up with some new model of attaining energy from fission, or potentially from fusion at some point, the dominant narrative, rightly or wrongly, is that it is a very good idea to shift away from building more nuclear plants, and to instead focus on the technologies that we know will work, and which do not leave any waste or other byproducts after the requisite hardware is built and initial infrastructure is installed. Unfortunately, those other options are hindered by their uneven, rather than consistent, output. Many of them only output energy under certain conditions, and thus, having energy backups is required to fill the gaps. Hence the popularity of lithium-ion battery backups. But lithium-ion battery production comes with its own collection of downsides. From a piece in Wired UK entitled "The Spiraling Environmental Cost of Our Lithium Battery Addiction." Quote, "In South America, the biggest problem is water. The continent's lithium triangle, which covers parts of Argentina, Bolivia, and Chile, holds more than half the world's supply of the metal beneath its otherworldly salt flats. It's also one of the driest places on Earth. That's a real issue, because to extract lithium, miners start by drilling a hole in the salt flats and pumping salty, mineral-rich brine to the surface. Then they leave it to evaporate for months at a time, first creating a mixture of manganese, potassium, borax, and lithium salts, which is then filtered and placed into another evaporation pool, and so on. After between 12 and 18 months, the mixture has been filtered enough that lithium carbonate, white gold, can be extracted. It's a relatively cheap and effective process, but it uses a lot of water, approximately 500,000 gallons per ton of lithium. In Chile's Salar de Atacama, mining activities consumed 65% of the region's water. That is having a big impact on local farmers who grow quinoa and herd llamas in an area where some communities already have to get water driven in from elsewhere." End quote. That same article goes on to say, quote, "There's also the potential, as occurred in Tibet, for toxic chemicals to leak from the evaporation pools into the water supply. These include chemicals, including hydrochloric acid, which are used in the processing of lithium into a form that can be sold, as well as those waste products that are filtered out of the brine at each stage. In Australia and North America, lithium is mined from rock using more traditional methods, but still requires the use of chemicals in order to extract it in a useful form. Research in Nevada found impacts on fish as far as 150 miles downstream from a lithium processing operation." End quote. Beyond the lithium itself, other fundamental ingredients of lithium-ion batteries, like cobalt, come with their own environmental and socioeconomic issues. Cobalt is found in quite large quantities in just one region, Central Africa, and in the Democratic Republic of Congo in particular. Because of the increased demand for these types of batteries, the price for cobalt has skyrocketed, and that has incentivized folks in the DRC to essentially just dig up their entire country, with many people setting up small mines on their own, digging up the metal by hand, and using child labor, often without any protective equipment, to do so. This is an issue because, in the words of Gleb Yushin, the CTO and founder of a battery materials company, cobalt is, quote, "uniquely terrible," end quote, in terms of toxicity. Many other metals are not harmful as they're being mined. That harmfulness only comes later, when they're being processed, if it comes at all. Cobalt, though, truly sucks from the very beginning, causing birth defects and breathing problems, and these ramshackle mines generally don't have any planning or safety measures in place. They kind of just dig with hand tools down hundreds of feet, and there are a lot of injuries and deaths, alongside the ecological devastation that occurs in a radius around these mines, and the longer-term consequences in terms of the locals' health. Thankfully, there are other options here. Options that, for the most part, are far less destructive to the environment and the people who work with the requisite materials and technologies than lithium-ion battery-based options. What I'd like to do is run through some of the more common, promising, and interesting options when it comes to energy storage systems, technologies that would allow us, or which are currently allowing us, to store spare energy that we collect via wind or solar or hydroelectric or whatever else, using mechanisms that are quite different from what traditional batteries of the lithium-ion or lead-acid variety can offer. Let's start with what's actually the most common form of this type of storage currently utilized for load balancing, which is the storing of energy produced during periods of excess to be utilized during periods of shortage. And that method is called pumped storage hydroelectricity, or PSH. PSH is a relatively simple concept in that it, at its most basic, simply involves pumping water to a higher elevation. But that simple act allows you to store energy in an easily reclaimable form. If you have electricity from solar power arrays that you do not currently need, you can use that energy to pump water up to the top of a mountain, where you have a holding tank, a dammed natural water formation, or even just a lake or other pool of some kind. That electricity powers the pumps that move the water to that higher elevation. And when you need it, you allow the water to run downhill, spinning turbines as it passes, converting that energy back into electricity. The round-trip efficiency of this storage mechanism is about 70 to 80% on average, which means if you use 100 megawatts to pump water up a mountain, you can expect to get 70 to 80 megawatts back when that water flows through those turbines on the way down. This system is simple, reliable, and efficient enough that it accounts for over 95% of all registered energy storage installations worldwide today. Unfortunately, it's also quite limited in that it's highly dependent on local geography. You need to have some relatively high elevations in the vicinity to make it work on scale. So it's a pretty solid option where it's feasible, but it is not feasible in most locations. And water tower-related alternatives, which can be built just about anywhere, are severely limited in the amount of energy that they can store in this way. That general concept of using energy to move things, or to change something, and then allowing those things to move back or change back into another form, making use of natural laws like gravity when you're ready to reclaim that energy. This is a fairly common concept in this space, and it is utilized in the broad strokes across several different storage concepts. A Swiss energy company called Energy Vault, for instance, is one of several companies building storage facilities that utilize concrete blocks instead of water, and cranes instead of pipes to store energy. This concept works by using excess energy to heft massive bricks or concrete or sand-filled oil drums with a crane, and then it stacks those bricks or oil drums atop each other into kind of a tower that surrounds the crane. So scaled up, this system looks a bit like a skyscraper made out of giant bricks or barrels, with a massive crane rising up through the center, poking its arm out the top. When you want to reclaim that energy that is stored in these towers, you grab the bricks or the drums with the crane and use a reversible motor to slowly lower them back down to the ground, collecting that energy back from the previous hefting in the process as those objects descend. A similar system, called rail energy storage, operates on the same general principle, but instead of hefting things with a crane and stacking them atop each other, you use electricity to pull a heavily laden train up a hill, and then you recoup that energy when it rolls back down the hill again. Gravity pulls the train downhill, and onboard generators capture that movement as it descends. Adjacent to those two concepts is one that's being developed by, among others, a Canadian company called Hydra Store, which uses excess electricity to run compressors that trap pressurized air in a heavily reinforced container. As that air becomes more and more dense, more compressed, it heats up, and that heat is captured in a nearby insulated hot water tank as the air becomes liquid. When they want that energy back, they release some of the compressed air, add the stored heat back to that air, and run the resultant pressurized gas through turbines to generate electricity. There are also a fairly large number of flywheel energy storage systems in use today, a system that involves spinning a rotor faster and faster and faster, and keeping energy within that system as rotational energy, rather than as potential gravity or pressure-based energy. Energy is extracted from this system by slowing the rotation a little bit, and it speeds back up, that rotor does, as more energy is added. Some energy will be lost over time using this system, and most of these types of rotors can only hold their spin at a usable rate for a few days, which is a stark contrast to towers and pressurized containers that have very little, if any, loss over time. But flywheels that use magnetic bearings instead of mechanical bearings, which removes much of the friction and points of failure found in the latter, can have a round-trip energy efficiency of 85%, which is very good. That means only 15% of the energy stored will be lost when it comes out the other end, reconverted back into electricity, as long as it is utilized within a few days of being stored, which is more than enough time for many potential use cases, most of which only require storage for less than a day. Despite being quite different in how they approach the problem, each of these energy storage methods are making use of natural laws to convert kinetic energy into potential energy, before eventually converting that potential energy back into kinetic. Or said another way, they capture energy and store it until it is needed once more, just like a chemical battery, but different in the storage mechanism, and in the inherent pros and cons. And make no mistake, there are significant downsides to these approaches, including in terms of their efficiency. The 70 to 80% that pumped storage hydroelectricity gets, the one where you pump water up a mountain, and the 85% that flywheels can get, are very, very good compared to other similar options. The compressed air method currently weighs in at about 60% efficiency at the high end, and that's if you're using the newer models. Other older versions of the same get something like 40%. Energy Vault, the one with the cranes and towers of concrete blocks, claim that they may be able to get 90% efficiency after they've had some time to refine their model. But that seems to be little more than speculation and good branding at this point, and it's a fair bet that it will be far less than that for the foreseeable future, just like with the train concept and other move things to a higher elevation concepts. They all have quite a bit of potential, but the practical application today is very low compared to other alternatives. That said, each of these models, including the lower efficiency ones, do have benefits over the others in terms of the cost of setting them up or maintaining them, the required infrastructure to get them going, or other considerations like where they can be built, where they can be established and operated. Running a train up a hill requires a hill, and pumping water to a higher elevation generally requires both that elevation and lots of water. Compression and stacking methods, in contrast, could potentially be established just about anywhere if you've got a little bit of land and can build the crane or the compression chamber. Thermal batteries are another promising direction that this field might take in the near future. One of the simplest and most straightforward manifestations of this concept is what is often called seasonal thermal energy storage sites, which utilize different materials in different locations to store heat, or in some cases to store cold, which is usually accomplished by removing heat, shifting it elsewhere, and then utilizing that heat energy to warm homes or to convert it into electrical energy. Some such storage sites are water tanks or insulated containers. You pump the heat in, derived from a variety of sources, from the sun to air conditioning units to factory machinery, and those tanks or containers hold that heat for a pretty good while due to their insulation and the nature of the warmed-up substance that they hold. Sometimes existing infrastructure used for other purposes, like underground oil storage, are used for this double purpose, holding heat in the oil while that oil waits to be consumed. While in other cases, detritus from construction, like reinforced chunks of concrete, are tucked away and used as heat storage mediums, rather than treating these chunks of concrete as just more rubble, destined for the landfill. Networks of corrugated plastic piping, buried underground, can hold hot air for a surprisingly long time, as can mere soil, piled up around a building. This is actually a traditional means of keeping some types of buildings warm in the winter and cool in the summer. You just pile soil up around the base of the building, and even more ideal, partially up the walls toward the roof, and you benefit from the difference in temperature seasonally, and in some cases the difference in temperature between day and night. On the more technologically involved end of the spectrum, it's possible to use molten salt to store energy in a similar fashion. Generally, using focused solar energy to superheat salt to around 566 degrees Celsius, which is 1051 degrees Fahrenheit, not quite 5 times its melting temperature, and then storing that superheated molten salt in insulated containers. That salt can then be piped into a tank filled with water to produce steam, and that steam can spin turbines, reclaiming some of the energy that was used to heat the salt in the first place. This option is already in use a few places around the world, but mostly on a relatively small scale thus far. Larger applications of the same concept could scale up the storage capacity and increase its efficiency, which is currently all over the map depending on what method and setup you use to reclaim the heat that is stored in the molten salt, but which is at an impressive 99% efficiency in terms of energy captured from the sun and stored as heat. So if they can convert that into electricity, even relatively efficiently on the back end, those who are in a position to use this method could be in a pretty good spot someday. One more primary direction large-scale energy storage infrastructure could lean is toward chemical and biochemical options, which include utilizing the sun to produce biofuels using algae and the like, but also potentially to take any kind of energy from any source to produce food, or the more energetic components of food, like sugars and starches. We could also take a longer duration approach and utilize energy collected from renewable sources to produce synthetic methane, which can, in turn, be converted into protein-rich food for cattle or for fish by feeding the methane to Methococcus capsulatus, a bacterium that creates edible biomass from any methane that it eats. In a lot of science fiction stories, space travelers subsist on some kind of uniform biomass that they can then convert into different textures and flavors to replicate various types of food while still providing the necessary nutrition on the cheap. And this is one way that we might do that, though in this case we'd be using that technology to produce biomass that can be stored and utilized later, either by other biological entities like humans or cattle that we might feed it to, or by some kind of power plant or other sort of energy reclaimer, so that the energy can be spent on all kinds of things, including converting its stored energy into electricity. We could also use energy generated from these sources to power water electrolysis, which can extract hydrogen from water by separating water into hydrogen and oxygen. H2O is 2 hydrogen to an oxygen. And that hydrogen could then be used as fuel, similar to fossil fuel-based energy sources, but with a lower output than input. So although this model of energy storage potentially allows our stored energy to be portable in a different way than other options, it's also potentially quite dangerous to transport, and its efficiency is quite low. The exact number differs based on the form and storage and extraction mechanisms that we're talking about, but on average it looks like you only get an efficiency of around 30% for hydrogen-based energy storage solutions, which is very low compared to other options. And although that could change substantially with time, according to some energy experts, it's also predicted to be a long-term thing, not something that would emerge in the next few years, especially since getting the most out of this method would require essentially transitioning to a hydrogen-based energy economy, so that we have the requisite storage, transport, and reclamation infrastructure in place around the world, which wouldn't really be practical, but would also create its own problems, similar to, but different from, the petroleum-based economic infrastructure, from which we are trying to shift away. At the moment, there are a lot of interesting options on the table, but no silver bullet, no single, ultimate, perfect means of storing energy during times of plenty, so that said energy is available to be used during times of need. That's not the end of the world, though, because just like with renewable energy sources, the idea is not to come up with one energy storage method to rule them all. Instead, what we've got are multiple potential paths that we can take, and that we are taking, and that we will continue to take. We will continue to walk all of these different paths, and other paths that emerge in the future, simultaneously. This is not a zero-sum game. So just as solar energy is unlikely to ever fulfill all of humanity's needs all by itself, until and unless we someday build a Dyson sphere, a structure that surrounds the sun and captures all of its energy output for us to use, which is incredibly unlikely in the next several centuries. But just like solar energy by itself is unlikely to fulfill all of our energy needs, so too are any of these energy storage options likely to fulfill all of our ambitions in isolation. Instead, we will use pumped water, spinning flywheels, liquefied salt, and anything else that we can dream up to ensure that we are able to get energy where it needs to be, when it needs to be there, and that we're able to do so, ideally at least, using the least possible non-renewable resources and losing the least possible energy along the way, in transit or while it's in storage. Right now, none of these methods gets close to the predicted $20 per kilowatt hour price that we will need to completely transition to renewables around the world. But as we iterate each of them and introduce new options and combine them in interesting ways in terms of storage combinations, but also energy production combinations, we'll get closer and closer to that price and bypass more and more of the hurdles that currently keep many areas from investing in these kinds of technologies, which in turn keeps them from going all in with renewables more broadly. The intercompatibility of all of these options, then, are in many ways more important than the functionality of any single one of them in isolation. That's not the way that they're likely to be pitched, of course, because our economic system requires that we talk about our businesses and inventions in a particular way if we want to get them funded, want to get them used, want to get attention for our creations that might otherwise go to other, better marketed options. But as we keep tabs on these types of technologies, in terms of assessment and in terms of investment, it's helpful to look at them as parts of a whole and to judge their worth as pieces of a grander machine, rather than as complete machines unto themselves. If you're enjoying Let's Know Things, consider becoming a patron at patreon.com/letsknowthings. There are also numerous other ways that you can help contribute to the perpetuation of this show. You can find those options at letsknowthings.com/contribute. The book that I'd like to recommend today is called Semicolon by Cecilia Watson. This is a relatively concise little book, but it's a delight to read. I actually listened to it, and there was a certain charm in that, because hearing about grammar and pedantry and things of that nature spoken by somebody else who knows exactly what they're trying to say and how and where the emphasis goes is quite interesting and fun. But the book itself is about the punctuation mark, the semicolon, and its rise and fall, its popularity and non-popularity over the years, the role that it's played in certain court cases, and how it came about in the first place. So if you're looking for something relatively concise, something that will not take ages to read, but that is nonetheless dense with information about a very specific topic, consider picking up a copy of Semicolon by Cecilia Watson. You can find out more about me and my work at colin.io. You can find the show notes for this episode and every episode of the show at letsknowthings.com. And you can find my blog at exilelifestyle.com. Feel free to reach out and say howdy on your social network of choice. I am at Colin is my name on most of those. Thank you so very much for listening. I'm Colin Wright, and I'll talk to you again next week.